Hello everyone. So welcome to this series of video lectures about maintaining air quality, which is actually the last chapter of your textbook. However, I think it's a good idea for us to start thinking about sustainability issues in our life. So in particular, I find this quite helpful to relate chemistry to our lives, to understand how chemistry can help us to understand issues like climate change, ozone depletion better. And maybe chemistry also holds the solutions for some of these issues that we currently face today, like air pollution, like climate change. How can we combat these issues using chemistry? Now, if you just look at the learning outcomes in the chapter 22 notes, which you have already received from me, there are a number of learning outcomes here. We will go through these learning outcomes one by one through the next 4 videos. So there'll be 4 videos in this series. You will need to have the chapter 22 notes with you as we go through these videos. So please have the chapter 22 notes ready now if you don't have it yet. Now, right at the bottom of page 1, I find this comic rather useful, a rather funny reminder of why we need science in our lives. Right? You notice there has been a lot of reluctance, a lot of inertia to get started on combating climate change. Now, climate change has been discussed all the way as early as the 60s even. Why has it taken so long for people to recognize the impact of climate change and to find ways to actually combat this issue? So as you can see, in this particular cartoon at the bottom of page 1, you can see that there's a lot of reluctance, a lot of procrastination when it comes to working on climate change. And so much so that really climate change is here now, right? It's not coming. Climate change is already here with us. And that's the reason why we need to study chemistry. Now, it is important to take note, sustainability is an important theme for your chemistry syllabus. What this means is that you should expect to receive questions on sustainable development, environmental sustainability in your O-level exams. So this is by no means extra information. You are expected to be very aware of environmental issues. And this is the reason why I would advise all of us to treat this very, very seriously for the exams as well as for our lives in the future. So let's move on. So before we study about air pollution, let's study what is clean air like. So we talk about air all around us and we hear this word atmosphere so often, right? So air is all around us in our atmosphere. So atmosphere basically surrounds the earth. However, the atmosphere can actually be divided into different layers as shown in the diagram. Now this is extra information, meaning it will not be tested directly. So you should have an awareness that the atmosphere can be divided into sub-layers. So we actually live in the troposphere layer right at the bottom, which is closest to the ground. But just above the troposphere is the stratosphere. Alright? And then we have the mesosphere, the thermosphere, and the exosphere is the very final layer of the atmosphere, which is very, very thin. And it's pretty much considered outer space. Okay, so the exosphere is basically what we commonly call outer space already. Now, importantly, the atmosphere is made of gases, different gases. But the most important part is the composition of the gases in air must be balanced. Okay? This means that the percentages of the gases in our atmosphere have to be maintained within this particular percentage range so that living things can survive. So now let's move on to page 3 to learn about what is the percentage composition of different gases in our air. So on page 3, right at the top, you see this very useful table which summarizes for you what are the percentage by volumes of the most abundant gases in our air. Okay, so first we have nitrogen gas. Nitrogen gas is the most abundant gas. Okay, because it takes up 78% by volume of clean and dry air. Now, nitrogen is actually a very important gas because nitrogen can be used to manufacture ammonia. So if you recall, ammonia has the chemical formula NH3, right? So to manufacture ammonia, we actually react nitrogen gas with hydrogen gas to make ammonia. And this process is called the Haber process. This process is named after the chemist Fritz Haber, who discovered this process. Okay? So nitrogen takes up 78% by volume of clean and dry air. The next most abundant gas is oxygen gas. As you can see, oxygen takes up 21% by volume of clean and dry air. Okay, so oxygen is not the most abundant gas. However, there is still ample, sufficient amount of oxygen in our atmosphere, and that is essential. Why is oxygen essential and useful? Oxygen is essential and used for aerobic respiration, which helps to release energy in our cells for cellular activities. Without oxygen, living things like humans, animals, plants will not have sufficient energy to carry out our usual cellular activities. Now, besides that, oxygen is also needed for combustion or burning. Okay, so combustion is a reaction whereby fuels react with oxygen to release energy. For example, the petrol in your car undergoes combustion in the presence of oxygen gas in order to release energy for the car to move. So petrol is an example of a fuel which undergoes combustion, and that requires oxygen. Now the next one is argon. Now notice how argon is quite unique in the formula. It is monatomic. So let's remind ourselves, what is the meaning of monatomic? Monatomic means it exists as single atoms that are not bonded. So why would argon exist as a single atoms? Because argon is a noble gas, and so it has a fully filled outermost shell. Okay, so argon is monatomic, Ar. So argon is a noble gas, and as you can see, the percentage by volume of argon is actually 0.93%. So this makes argon the most abundant noble gas. So notice how there is a difference now. The most abundant gas is nitrogen, but the most abundant noble gas is argon. So don't be tricked, because in MCQs as well as in paper 2, we often ask you, what is the most abundant noble gas? The most abundant noble gas is argon. Now argon is particularly useful because it's used to provide an inert atmosphere for reactions to happen. Okay? Now, if you recall from your EYE at the end of this year, you actually had a question right at the end of paper 2 that asked you, why is an atmosphere of argon used in the manufacture of the aircraft blades? Now, to manufacture aircraft blades, you need an inert atmosphere of argon. This is to prevent the metals, the reactants, from reacting with water or oxygen in the air. So we use argon for this purpose because we know argon is a noble gas. It has a fully filled outermost shell, and therefore argon will not gain, lose, or share valence electrons with other elements. Therefore, argon will not react with our reactants. It will prevent our reactants from reacting. Alright, and that can be useful, especially if you want to prevent impurities from forming. Okay? So argon is the most abundant noble gas. And thereafter, we move on to carbon dioxide. Now, you would have been familiar with carbon dioxide as a greenhouse gas. However, carbon dioxide is actually naturally present in clean, dry air. Okay? The percentage of carbon dioxide is about 0.03 to 0.04%. Now, from this alone, you can tell that air is a mixture. How can you tell from these percentages alone that air is a mixture of gases? Because you can see that carbon dioxide has a range of percentages. This means that there's no fixed composition or ratio of the gases. Sometimes carbon dioxide could be as low as 0.03. In other samples of air, the carbon dioxide could be as high as 0.04. So there is no fixed composition of gases in air. Okay? What that means is that it's not one single percentage for each gas. There can be a range, as you can see from carbon dioxide. Now, carbon dioxide is naturally present because carbon dioxide is essential for photosynthesis. Okay, so plants take in carbon dioxide gas from the atmosphere. Plants take in carbon dioxide gas in order to produce glucose. Glucose is the organic chemical which is a source of nutrients and energy for the plants. This process of making glucose from carbon dioxide in the presence of light is called photosynthesis. So you should be familiar with photosynthesis. We will discuss photosynthesis again in lecture 4. Now, besides being essential for photosynthesis, carbon dioxide is also needed to maintain the surface temperature of the Earth at 15 degrees Celsius. Now, 15 degrees Celsius is an average across the entire Earth. Of course, in Singapore, it's not 15 degrees Celsius because Singapore is very near the equator. It's in the tropics, so it's very hot. However, as an average of every single point on the Earth, from the North Pole to the South Pole, the average is typically about 15 degrees Celsius. And this is crucial. We need CO2 to maintain it at this temperature through the natural greenhouse effect. CO2 traps heat in the form of infrared radiation on Earth. Alright? So CO2 is crucial and useful. Without CO2, the Earth will be too cold to support life. Okay? However, of course, as you know, the problem is we have more and more CO2 in our atmosphere due to increased use of fossil fuels in the past 200 years. Okay, as the amount of CO2 in the atmosphere continues to increase dramatically, now what we have is the enhanced greenhouse effect, which we'll discuss in lecture 4. Now, the final gas in air is called radon. Now, radon is actually a noble gas. It's a radioactive noble gas. And this is crucial. Radon is present in the air in trace amounts and is responsible for background radiation. This is the radiation that we are naturally exposed to. It is not because there's a nuclear power plant, there was a nuclear bomb. No, there is naturally radiation occurring in nature. This is perfectly natural. It's perfectly part and parcel of life. And the background radiation that occurs naturally is due to radon gas in our atmosphere. Okay? Radon undergoes radioactive decay, and in the process, it releases energy in the form of radiation. Now, it is important for you to learn the percentage by volumes of every one of these gases, as well as the uses of each of these gases. Please spend some time learning this thoroughly. Now, we know that air is a mixture of these gases, meaning the gases are mixed together in no fixed ratio, and their gases are not chemically combined together. So the nitrogen, oxygen, argon, they are not chemically combined together. Therefore, we can actually separate the mixture, air, into its components gases using fractional distillation. Fractional distillation is the physical separation technique which is used to separate air into the component gases. Why is fractional distillation a suitable method to separate air? So if you think back to chapter 1, when do we use fractional distillation? Why is it suitable? It will be suitable if the components, in this case, the gases in air, are miscible. So all of the gases in air can mix together. They do not separate into layers. Alright? The nitrogen, the oxygen, the argon, they can all mix together. So they are miscible. So the gases in air are miscible, and importantly, they have different boiling points. Because they have different boiling points, they can be collected at different sections of the fractionating column. So if you recall back to chapter 1, when we did fractional distillation, we said that there must be a fractionating column. So this over here is the fractionating column or fractionating tower. Okay, so in the fractionating column, you actually can collect different gases based on their different boiling points. So let's go through. It looks a bit blurry, the diagram. So let me talk you through the diagram. So the air enters from the top here. So that's the mixture air. Now importantly, once it enters the fractional distillation setup, the air will be compressed and cooled. So if it's too small, you might want to write down cooling and compression. Cooling and compression of air. Now, what is the purpose of cooling and compressing the air? By cooling and compressing the air, you are liquefying the air. Meaning, you convert the air into a liquid. And this is crucial. You need to ensure that it's a liquid before the air can enter the fractionating tower. If you recall, fractional distillation separates the gases based on boiling points. You need the thing to boil. What can boil? Only liquid can boil to form a gas. If it's already a gas, there's no more boiling, right? It's already boiled. So now you need to liquefy it so that it's a liquid so that it can boil. Now when you cool it down to how low? Typically, it is cooled to minus 200 degrees Celsius. Alright, negative 200 degrees Celsius. 200 degrees below zero. That's how cold it is. Now at this temperature, not only do you liquefy the air, at this temperature, the CO2 turns into a solid. Okay, so if you recall, carbon dioxide actually does not have a liquid state under atmospheric pressure. Carbon dioxide sublimes, meaning solid CO2 directly turns into a gas. Similarly, gaseous CO2 directly turns into a solid, and this is of course called dry ice. So CO2, when it's solidified, is called dry ice. Because it's a solid, it can be removed by filtration. So the solid CO2 is removed by filtration. Now this is crucial because if the solid CO2 is not removed, the solid will clog up the pipes that you can see in the diagram. So it is very crucial for the solid CO2 to be filtered and removed to avoid clogging and blocking the pipes. And finally, after removing the CO2, the remaining air mixture, which is now a liquid, is passed into the fractionating column where it separates out based on its boiling points. So, nitrogen gas has the lowest boiling point of negative 196 degrees Celsius. Because it has the lowest boiling point, it's collected at the top. Lowest boiling point is always the top fraction. So this is an important thing to remember. The lowest boiling point substance is always collected at the top of the fractionating column. Conversely, the one with the highest boiling point is collected only at the bottom of the fractionating column. In this case, it's oxygen gas. Oxygen gas has the highest boiling point and is therefore collected at the bottom of the fractionating column. Now, you need to be able to describe the process of fractional distillation of liquid air to separate air into its component gases. So ensure you know whatever I've written on this screen. Take the time to annotate your notes at the bottom of page 3. Pause the video before moving on. Okay, so I hope you have taken down the annotations on page 3 thoroughly. Everything has to be learned. Now let's move to the final part of this video, which is page 4. Now, we can do some experiments to prove that air indeed has this percentage composition for each gas. For example, how do I prove that oxygen is 21% of air? Well, one type of experiment involves heating up copper metal with air in a syringe. So, as usual, in a question, let's highlight numbers. Let's highlight chemical names. So 200 cm cube of air, highlight that. Copper, highlight that. So 200 cm cube of air was passed over heated copper in a syringe until the reaction was complete. In order to figure out what's going on, you need to know what is the reaction. The reaction is copper plus oxygen in the air. So of all the gases in the air, copper reacts with oxygen. Okay? It does not react with argon because argon is a noble gas, already has a fully filled outermost shell. So argon doesn't react. Nitrogen. Nitrogen is also unreactive with copper because nitrogen has a triple bond which is very difficult to break. Therefore, nitrogen gas is very unreactive compared to oxygen. So of all the gases in the air, oxygen is actually the most reactive gas. So copper reacts with oxygen to form copper 2 oxide. Remember, copper 2 oxide means copper is +2 oxidation state. Of course, this is not a balanced equation. There's 2 oxygens on the left. I only have 1 on the right. I need 2 in front of the CuO to balance the number of oxygen. If I put a 2 in front of the CuO, I need to put a 2 in front of the Cu as well in order to balance the number of copper. So now that we know this is the reaction, let's make sense of it. So copper reacts with oxygen. Tick. The next question to ask ourselves, air. How many percent of the air is oxygen? 21% of air is oxygen. How much air do we have? We have 200 cm cube, meaning 21% of 200 is oxygen, meaning 21% times 200 equals 42. So there is 42 cm cube of oxygen present. Hence, what does the question want me to calculate? The question wants me to calculate the final volume of air remaining. Remaining is the key word. Remaining means everything that is left except oxygen. Because the oxygen reacted with copper is gone. So what is remaining? Nitrogen, argon, carbon dioxide, radon, basically everything except oxygen. So the final volume remaining is just the initial volume, 200, minus 42, which is the volume of oxygen. So 200 minus 42 equals 158 cm cube. Alright, now I would advise all of us to do checkpoint 1. Try checkpoint 1, see if you are able to obtain the answer. Okay, the answer is B. Okay, but let's see whether you are able to obtain the answer. Okay, if you have understood this video, the concepts in this video, you should be able to do checkpoint 1. Okay, now this brings us to the end of this video. If there's anything you're unclear about from pages 1 to 4 of the notes, please rewatch the video. If not, please also clarify and check in with me if there's anything you are curious or doubtful about. Thank you and see you in the next video.